1955, this clock, this is the first cesium clock, was invented at at NPL UK. Like this is the same name. It was first established the National Physical Laboratory at UK. Then during British era 1947, 44, it was in Delhi. So NPL UK, there is two great scientists, Louis Essen and Perry. They invented this first atomic clock, that is cesium atomic clock, in 1955, and later on 19 I think 57 or 59, they were awarded Nobel Prize. And this is a famous statement. So they invited the director of the NPL UK, and he said that it was obvious from the very first moment of operation that we could set the quartz clock with the greater accuracy with the microwave clock, and we invited the director to come and witness. Just see the line. Witnessed the death of an astronomical second and the birth of the atomic time. So that was the birth of the atomic time, atomic clocks in 1955. But then after it get commercialized, we have a very compact view of the cesium atomic clock. This is the beam clock. And now we will talk about some technical terminology, that accuracy, uncertainty. So this clock is having accuracy or instability of 1 parts of 10 to the power minus 12. So if you run such a clock over a period of 30,000 years non-stop, then only you can make a mistake. Either you can gain or lose 1 second of time. So 1 second error can arise only after 30,000 years of continuous operation of such clock. So this is the level of accuracy of such atomic clock. So at CSR and NPL, I already mentioned that we are responsible for realizing our international time, that is called UTC NPI, and also Indian Standard Time, and we use 5 such cesium atomic clocks. And if there is a process, we just use some algorithm to combine the output stability and then finally realize to another frequency source, that is called hydrogen measure. And this Indian Standard Time or UTC NPL is always comparable, always being compared with the international time, because if somehow we measure wrong 1 second, then our minute day will be a bit longer or shorter compared to the other community. So all the time, 24/7, 365 days, the second we realize, the second we generate, that is being compared with the other international community. There is a meteorological society head called BIPM. So this is a two-way satellite time transfer system and global navigation system, GPS system. So that are being used to compare our time with the international community, and that's being happening all the time. These are the, if you some of you, if you have scope to come to NPL, just contact us. We will show this facility, and in the rooftop we have this antenna. And not only that, then we transfer the time to the user of that country. So like if anybody requires time within accuracy of millisecond, then they can simply use this NTP server just through internet. In your computer, you can all sync with our NPL time, and that can give you millisecond accuracy. But if somebody really requires nanosecond accuracy of time, then we have a special technique, and that's a dedicated service. Our people can help, and we can establish this nanosecond accurate time. So I can show that this is the facility, and in 2021, our Honorable Prime Minister, he dedicated this service to the nation, and we had a function here. And but although some of the minister was present in NPL, you see our Education Minister Dr. Harshvardhan was there, but Honorable Prime Minister, he came to the online, he virtually appeared here. So this is the same service we are talking about, and this is the link uncertainty. We hold a very stand firm compared to the other international organization. Now we talk about the microwave cavity. So the cesium is passing through the microwave cavity. Now if think about the simple principle of the Heisenberg uncertainty principle. So delta P delta x equal to h cross by 2 is to be greater than less than or equal to. But similarly, we can see delta T delta E. The other way, E is the energy, that is equal to frequency. So if you have a larger uncertainty in time, you have lesser uncertainty, energy or frequency. So if this cesium beam takes longer time to cross this microwave cavity, then it has a longer time uncertainty. It means it will give you shorter, very small uncertainty in frequency. So that's what people try to do. So they started building longer microwave cavity. So it means that cesium atom will take more time to travel through this microwave cavity. So in that way, you can have a better frequency reference and you can measure the time more accurately. So from the normal beam clock to this kind of long tube beam clock, the accuracy is like 3 to 4 times better. Now we have a it's few times a second order better. I mean, actually you have a stability is of the order of minus 14 or uncertainty. And then if you run such a clock over a period of million years, then only you have an error of 1 second. But we are talking about 1 second error, but there is a chance that you can make an error of nanosecond, microsecond. So then this million years is not anymore million years, it's in few years and days. So that is the catch. We are talking about 1 second, that's a big error, that is not acceptable. So that's why you see 1 second error in 3 million errors. Okay. Similarly, we can think about another thing, that instead of increasing the length of the tube, we slow down the atoms. That slow atoms will go very slowly and it will take longer time to cross the microwave cavity. And that exactly we do with laser cooling. So in 1980, I mean around 80, so laser cooling was invented. And then people thought about, okay, why we need to increase the length of the cavity? We can simply use slow atoms. The atoms are moving very slowly. So it will take a longer time to interact in the microwave cavity, and in that way you have better accuracy in the clock. So, but people might be wondering, we know laser is a source of energy, it's a photon. So when it shines on something, if it is absorbed, it gives some energy. How come it can cool something? It's a bit strange. I mean, laser is used for cutting a metal. It produces a lot of heat. I mean, we know about the laser ablation experiment where we shine this laser on a metal and it produces vapor gas. But how come the same laser, same sort of things can be used for cooling, lowering the temperature? Okay, so then I'll simply say how it works actually. So we are familiar with the Doppler effect. Okay, so if an atom is going with some velocity in this direction, let's say in my towards right, towards this arrow, then it has a resonant frequency of nu or omega, so it will not absorb this photon in the same frequency because of the Doppler effect, it will absorb in the lower wavelength, lower frequency. So on the other hand, if the laser is going to the same direction, the atom will absorb it is in the higher frequency because of the Doppler effect. But these atom and photon, when they interact, the atom absorbs the photon, but photon has a momentum. We know a photon with a frequency of nu has momentum h nu by c. So the atom absorbs this photon. It means it gets a momentum from this photon, and it gets kicked from a particular direction. But while it is emitting here, Laura, you see, it's emitting spontaneously in all directions. So it is actually continuously getting a kick from this direction. So in that way, if you can absorb different atoms on all 6 directions, so it will start getting momentum, kick from the all directions. So this photon actually slowly reducing this kinetic energy. So it's become slower and slower. So this is the principle actually. It reduces because why? So because of the Doppler effect, it is absorbing in lower frequency and emitting in the higher frequency. So if you are absorbing lower frequency, absorbing less energy and emitting high frequency energy, so this energy must coming from your inside. So the atom's internal energy getting reduced. Internal energy is giving you kinetic energy. So atom is not anymore in motion. It becomes slow and slow. So that is the principle of laser cooling of atoms in very simple way. So these laser cooled atoms are being used, and that is called as a cesium fountain. So why fountain? It's a very simple reason, because it looks like I'll show you some animation here. So this is like a group of atoms being collected here and being laser cooled with 6 pairs of laser, and then it is tossed up. Then it is tossed up towards up because of radiant radiation, and we have the microwave cavity here. So atom goes up slowly, and again it falls down because of the gravitational pull, and again it's passing through the microwave cavity. So earlier we saw a microwave cavity of U shape. It was interacting twice. Here also, this cylindrical cavity, here atoms are interacting twice, and it is absorbing in the right frequency, and it's a different kind of technique where we detect whether it absorb or not by its laser spectroscopy. So now we tune the microwave frequency in the right way, right direction, that we can find the resonant frequency. So this is cesium fountain, and this is a animation. You can, if it works. No. Yeah, it works. So this is atoms are going up and coming down, and we shine the laser. So this is again. So it when atoms goes up and coming down, it looks like it's spreading like a fountain. So that's why it is called atomic fountain or cesium fountain. It is being done with the cesium atom. So that is a cesium fountain. Okay, so I can show you some of the picture of the cesium fountain at different countries. This is India and in NPL, and it has a typical accuracy of the order of 10 to the minus 15. That means if you run this cesium fountain over a period of 30 million years, then only you can have a chance to gain or lose 1 second of time. This is the cesium fountain. Only few of the countries could develop such a state-of-the-art technique, and India is one of them. And we have the first operational fountain in 2015. So this is in France, this is in East Boulder, USA, and this is PTV Bronzing in Germany. And there are few. I think at present 7 to 10, 8 to 10 countries have such facilities. Okay, so now you may be wondering. So we are talking about a clock with accuracy of 1 second inaccuracy in millions of years. So do we really need such kind of accurate clock, or what is the usefulness? What is the utility of such a good clock? Or just for curiosity, why people are building even more good clocks? So I can show a very simple example which we practically use in our daily life, like for the navigation. We already talked about the sea navigation, but like surface navigation. So being located in Delhi, we can see I am somewhere here, or anybody is somewhere. So he's a newcomer and does not know. Nowadays we are seldom using this GPS facility. But how GPS is helping you? What is the basic principle? Again, it's accurate time measurement or accurate time keeping. So let's say this person is standing here and he is curious to know his position very correctly. So we choose three different places with big towers in Delhi. This is Qutub Minar, and this is the tower in Pitampura, and then we have three time emitter in the top of the towers. Okay, this signal is transmitting here. The time is coming from here, and this person has a handheld device which can receive the signal, and it can measure the traveling of time period. Like if the signal started from 10 a.m. and it is arriving at 10.02 a.m., 0.02 minute or 0.02 second is the time of arrival from here to here. So you can calculate with the speed of light. Let's consider the signal is traveling with the speed of light. So we can calculate the distance, and now you can easily say that this person is somewhere in this radius. You cannot pointing him out in a particular place, because this is a radial distance, you can say. So this person must be locating somewhere here. In order to know his position very correctly, so we are taking the signal from the other tower, and now it gives another radius. So this radius is intersecting in the two different points. So we have probability that this person might be here or here. But if we take the help of the three towers, then they are interacting in a single place. So that will tell you his position. Now you see, light is traveling with a speed of 3 × 10⁸ meter per second. So any inaccuracy in the time measurement, let's say 1 second is a very big number. Again, I'm saying like 1 nanosecond, if it time inaccuracy measurement will give you a positional error of 0.3 meter. It's just simple. So here our accuracy, like if it is a meter, then then you need time with accuracy of nanosecond. It's a nanosecond accuracy. But if you need precision of millisecond, not meter, sorry, in millimeter, centimeter, then your time should be of the precise of 10 to the minus 12 at least picosecond. So that is one of the use. I mean, we can correlate with our requirement. Same thing. I mean, we take it granted like GPS. Everywhere while we are driving, we are going to new city or new places. We don't bother to carry a map or don't need to ask anybody about the location where we want to go, because GPS is guiding us all the time. And fortunately, GPS has a very fantastic orbital distribution. It has 6 different orbits with 45-degree inclination, and each orbit has a 4 satellites all the time. So we have always visibility of satellites. Then same principle, we need at least 3 satellites to know our position very correctly in 3 dimensions. But here there is a catch. Let's say if the clock of your device, what you are using, nobody guarantees this. GPS time might be correct, because for GPS there is a US Navy, they are taking care about the onboard atomic clocks. But who takes care about your own clock, the device clocks? It may be wrong. It can give you some wrong time. So if your device time is not correct, it cannot measure correctly the time of arrival. So for that, you need to correct your time of the device, and you need another satellite. So that's why you need at least 4 satellite signal to know your position time very correctly. So this is the principle, and where time is nanosecond, sub-nanosecond accurate will give you precision of sub-meter. Okay. So this is time synchronization business. And then another critical application we can think about, like surveillance or defense, like a radar. We know the radar, how it works. In the radar, we actually sign a microwave signal or any infrared signal, whatever it is. So it is goes there and it's signed back and reflect back from the target. So you can measure the time of arrival from the time you send the light and you got it returned. So that arrival time, just travel time, telling you the distance, and you know the direction, so you can calculate its position. But now this problem is many of the projectile, their metal, their surface is not reflecting the signal. So they have improved their things, and there is a lot of R&D on that. So you cannot use this conventional radar on those things. So what we'll do, we will use the passive radar. Passive radar is nothing, any object, anything in the world, they have some emission, and you don't know in which wavelength. So let's say it's in a particular wavelength, a particular frequency, and we have distributed sensor. We put different sensor, and we observe what are the frequencies coming, and then we correlate time of arrival of the signal. Same signal when arriving. So I can show you. This is a kind of passive radar. You can bring it to your location and start monitoring. So how like there are 2 sensors, like sensor 1 and sensor 2, and there is an emitter. The signal from this emitter, it arriving here first, then it is coming second here. So this is the difference of time of arrival, which will give you a hyperbolic transition. It's a trajectory, hyperbolic trajectory. So if you use 3-4 such things, we have a common interaction point, and then only you can measure the time. So in this technique, we have calculated, like let's say this projectile is like more or less 200 kilometers away from the surface. Then what will happen? For 100-meter accuracy, you need 1 nanosecond accuracy in the time. So for a positional accuracy of 100 meter, you need 1 nanosecond accuracy in the time. And for defense, is very critical. So there also they need a clock with sub-nanosecond uncertainty or better accuracy. So this is one of the reasons people are still thinking about better clock. So we have already discussed about the microwave clock, cesium clock. Can we make it better? Yes, we can do, because if you think about the principle of a clock, this is, we call it Allen division or instability or inaccuracy. It defines by the delta nu. Delta nu is the transition line width, and by nu zero, that is the transition frequency. So if you have a narrow line width, you have a better clock, But if you have a longer, higher frequency, then you have better clock. So microwave like 10 gigahertz cesium clock. If we go to the optical, that is 10 to the power hundreds of terahertz, obviously these clocks becoming more better. It's become more accurate. So that's why people are started working towards building a clock where the atomic transition is happening in the optical domain, not in microwave domain. And I can tell you, and within let's say within 10 years, because this is a long time in discussion, the present SI definition of time, the present standard of SI second, is based on the microwave transition of cesium, cold cesium atom, that is the cesium fountain, that is the primary clock. But in near future, it will be defined on the basis of some of the optical transition, some of the optical clock. Which optical clock? That is the entire world is working. There are many candidates, it can be more than one, it can be single, that is not decided yet, but there are several potential candidates. Okay, I can discuss a little bit. So in which way the time will be defined, the definition of time, that is SI second. So I can show you, this is the atomic era 1955. Then clocks is getting better and better because accuracy or uncertainty is getting less and lesser. So this is the microwave clock. So let's say 1955 to 2015, it is coming from 10 to the power minus 10 to 10 to the power minus 15, lower part of close to 10 to the power minus 16 or 10 to the power minus 15. But this optical clock business, it all started, or people think about it, it's after the laser cooling and all the advanced technique. So it started around 1990, let's say. The last less than 30 years, it is like again started in the same point, but it is reaching to 10 to the power minus 18 or lower part, or it's already. This is bit like 10 to the power 2014-15 data. So recently somebody has reported like lower part of 10 to the power minus 19 also. So this is so fast and so better. So what is the possible way of building an optical clock? So optical clock can be built with neutral atoms. You can trap the atoms in an optical lattice, in an optical field, optical potential, and then you can interrogate the atomic transition in the optical domain. So there are plenty of candidates like hydrogen, magnesium, calcium, strontium, ytterbium, silver, many others. But it has an advantage that you can, these are neutral atoms, so you can accumulate large number of atoms together and you have very good signal to noise ratio. But since you have a large number of atoms, their coherence times is limited. So you cannot run this experiment at a single time very long. So that is one of the disadvantages of this technique. But there is another way of doing this optical clock, that is single ion. Ion is a charged particle. So you cannot bring many ions together because that is a Coulomb force that will give some erroneous result. So one ion is trapped in within an ion trap, then do it laser cooling, that is a stationary ion, and you do the optical clock business. So there are again few candidates, ytterbium, strontium, mercury, aluminum. These are the very potentially strong candidates to be primary standard of the time and frequency standard. And here in CSR NPL, we are working with this ytterbium 71, this ion. So as I discussed, there are many candidates. We are not go individually one by one. Simply, I will show few minutes or in the slides about our activities towards building an atomic clock in the optical domain, that is called optical clock, with the help of a ytterbium ion, and the transition frequencies of 35 nanometer. That's designed ion trap with the RF and DC. So that will help you to trap the ion inside the center of the trap. Then we need to do the laser cooling. So this has a very complex atomic structure. We need multiple laser, 4 or 5 different laser for doing the laser cooling. So that's detailed, but we are arranging this optics for doing the laser cooling, and it's nothing. It's just cooling down its internal energy, bringing it to the rest. So there will be no Doppler effects. That is the reason we are doing the laser cooling. Then we are talking about a transition of line is 1 hertz, but none of the laser, none of the optical source has 1 hertz line. So we need to build a special laser system and special laser cavity that is called ultra stable probe laser. which will give you a very narrow line like this. So that is another thing we have to carry. We are still not started this thing. Then the clock will started working. We have the frequency, but what is the line of the frequency? What is the number? Who tell you? So then we have a optical frequency counter that is known as optical frequency cone. So there only you can measure the transition frequency very correctly. These are the two parts we have to develop or we have to arrange. Now, I told you that you cannot trap a ion in 3 dimension with DC electrode because DC can give you 2 dimensional confinement. So then we use, this is kind of oscillating trapping potential. It is the use of the RF, radio frequency high voltage, which actually give you this kind of oscillating trapping field. So you see that the trapping potential, if it's dancing in all 3 dimensions. So whenever this ion trying to escape through the shallow point, the field surface is changing. So in that way, we are confusing this ion. So it is being confined in the trapping potential at the center of the trap. But it is not fixed. It is like dancing a little bit slowly. And this is dancing speed. It depends on the RF potential or RF frequency. Next part, I'll show you how this trapping potential works. So this is, you see, we produce the ion and we trap it here. Then we are using multiple laser for doing the laser pulling, and this different color of this line is presenting actually to 3 different laser. And what happened? You see, initially the ion was moving like this circle, blue circle. It's the ion. It is like dancing and moving around. Then because of the laser cooling, it gets slowly, and now it's almost in rest. So this is a cold ion with a microkelvin temperature. So this is a kind of Doppler probing we can do. So now we can ready our fog laser and with the detector and tuning the frequency, we can detect, oh, this is the right frequency we are signing. And this kind of clock can give you accuracy or stability less than 10 to the power 17, 18 nowadays. It's easy. And it is like, it is factory. This kind of clock does not give error in a real sense. It's like few hundred millions of years or billions of years, you can get 1 second inaccuracy. So this is, I'm going bit fast here because I told you this RF potential, this is playing a crucial role here for trapping the ion. And high voltage, like 1 kilovolt RF, you cannot directly connect to the trap. So this is one of our resonator we build here, which actually deliver high voltage RF to the trap. And here it is inductively coupled. So inductively coupled is the advantage. It will never give you the reflected signal to the source. So your source is secure, and you can do the impedance matching by just moving these two coupling coil. So you have best probable coupling and best probable high voltage RF delivery. And you see, this is, we are talking about trapping of single ion. So it's a very special design. And once you have an ion, and it should be kept inside a vacuum chamber of the pressure of like space, जहाँ पर practically कुछ नहीं, 10 to the power -11 millibar or -12 bar millibar. Because if there is any residual gas, so they will knock this ion out of this trap system. So you are keeping things in, nothing is absolutely vacuum, but like space-like atmosphere. And this is a tiny electrodes here with a separation of 700 micron. You can see this is our design of the chamber, UHV chamber, and we have this. This is the atomic oven. We are spraying the atoms in the trap center. Then we're doing all the laser cooling. So this is the trap center we are presenting here. So all the laser is shining like this is 700 micron, and you have to accumulate 5 to 6 laser at the center. So it is not, its alignment is it's a very mammoth job actually. Like making the beam such a narrow and focusing in the center. It is not hitting anything because you need to monitor the fluorescence of the ion, and one single ion will give you like few hundred photons per second. So detecting them is again very challenging. So then this is the pumping station where we have connected just to get the UHV condition, and I can show you some of the laser system because we do a lot of frequency modulation through AOM and UMM in the range of several megahertz to several gigahertz. This is too much of detail. I'm not showing those details, experimental detail, but I can show in principle how it looks like. So this is this RF resonator. We are connected here, and this is giving the high voltage RF. and we have taken the high resolution, very magnified picture of this ion trap inside the trap chamber. And these are the two electrodes, the separation between the inner tip. You see, this is the outer electrodes, and there is a center, there is a rod. So their tip to tip separation is like 700 micron. And I can show you how it was. So from here, the atomic oven is spraying the ytterbium atom. Then with the use of two laser, we are producing the ion. Then ions are being trapped here inside the trap chamber. This is the trap. This is the housing of the trap chamber, and this is the trap. So the trap inside this ion trap, the ion is trapped. And then we are arranging this all the lasers for laser cooling and introduction. And I have already admitted that the clock laser is yet to build or yet to get. So we are preparing with the ion trapping and laser cooling part only. And this transition frequency is around 435 nanometer, and overall uncertainty or instability of the clocks we are targeting is 10 to the power minus 18. So this is kind of what we are carrying in India towards building an optical atomic clock or optical clock, which will be the future definition of the SI second. There is some few reprinted recent publications. We have few, and I would like to thank some of our senior colleagues like Dr. Sengupta. He was the mastermind and who actually initially thought about this facility to be built at NPL. Unfortunately, with the time, he superannuated, but still he is with us for every help. Then Dr. Manoj and Dr. Subhasis, they are also actively helping and participating in these things. And few of our students here, Neha, Otis, and Loki, they have already got their PhD and presently doing their postdocs and abroad, mostly doing some services. And then these are the 3-4 students, Harish, Suam, Nilam, and Pallav. And they are working in different aspects of this ion trapping and time transfer of this different activities. So again, finally, I think I'm running sort of time right now. It's almost covering, so I'm within time. So this is, you see, 1.6 10 to the minus 10 millibar last month, but right now our system is reaching 10 to the minus 11, lower part of minus 11. So we have achieved the targeted vacuum level almost, and then we are producing the ions, and I have some process spectra of the ions and all this thing. So this is all too much detail. So this is whole about the evolution of the time and frequency standard or clock, how we started from the obelisk in the ancient time during the Sumerian, and now slowly to going towards the atomic clock standard to the finally optical clock or optical frequency standard. So thanks to all of you for your kind attention, and again for giving me the opportunity to interact with you. Any question, any queries, any discussion is welcome. And now the floor is open for the discussion. Thank you.
Yeah, thank you, Dr. Subhasis. Yeah, that's a very excellent talk on the importance of the time, the evolution of the timekeeping, and like how the scientific development has helped us to get the accurate timing over the million years. Like it's very excellent talk. Yeah. The talk is open. The session is open for the questions. I will take question from the offline audience. Anybody? Yeah. So we have Pradeep has a question. Dr. Pradeep is here.
Okay, so thank you for the nice talk. So this is like so you said that you have this error of chances of error of 1 second, let's say in the 30,000 years.
Yes.
Right.
Yes.
So is it possible that you can have error of let's say 4 seconds in the first 30,000 because it's a probability, and the next 90,000 years you don't have any error?
I mean, what we are talking about is average. I mean, overall performance or overall inaccuracy. Actually it is impossible to run a clock for 30,000 years. So we actually in practical sense, when we talk in terms of technical discussion or technical group meeting or technical committee, we talk about the error in terms of nanoseconds. So how many nanosecond errors in every day? That is the quantity we define. So this 1 second error in 30,000 years, it is the exaggerated value of few nanoseconds in a day. It's nothing else. So that is the practically what we see and what we deal. Really, what we deal, it's like nanosecond drifting and nanosecond error in a day. But 30 seconds, if you talk to